What's up? Welcome to Backend Stuff. I'm Jacob Blitzo, here to help you build tech for the future. Think about scalability, reliability, and cost. If you want to learn how to build scalable, production-ready APIs, hit that subscribe button now. This is episode 11 in Elixir Basics. Today we are diving into bitstrings. What is a bitstring? A bitstring is a fundamental data type in Elixir. It's denoted with double chevrons on each side of it. A bitstring is a contiguous sequence of bits in memory. Let's go ahead and open up our terminal. And I'll make this bigger so you guys can see it easier. Okay, let's go ahead and CD to our desktop and then make a new project. And I'm going to do mix new and call this one bitstrings. And let's go ahead and CD into that directory bitstrings. And let's get our Elixir shell up and running. So IEX space dash capital S space mix. And now we're in the Elixir shell. Bitstrings allow us to work with binary data effectively. Binary can be really hard to read, especially quickly. So if we do something, whenever you are writing a binary value in Elixir, you have to start it with a 0B. And then everything after that is the binary. So if we did something like 110, that is the value of 6. So if you're not familiar with binary, the very first value is 1. And then the second one next to it is double the value it just came from. So that's 2. And then so on. So double 2 is 4. So you have 1, 2, 4, 8, 16, 32, and it goes on and on. So this is 6, and it's obviously not hard. We have bits 4 and 2 enabled and added together. But working with full bytes or any kind of binary manipulation, this can get complicated real fast. If we wanted to depict this in a bit string, we can do something like this. We can just do the double chevron, and then we can put in our same value. So 0B110, and then we're going to do a double colon and the size of our binary value, which is 3. So we're only using 3 bytes, and then the double chevron to close it off. And now if I hit enter, we see the value 6 and the size that this bit string takes up, which is 3 bits. So we can do a lot of things here. We can do things like this. We can do this binary 6, so 0B110 is 3 bits. And we can say, is this equal to the double chevron, 6 double quotes, or double colon, bit size 3, and then the double chevron again. These two values are equivalent. So they both get broken down into, binary bytes and comparator bits. And so that is true. And we can even do things like this. So shorthand, just the double colon 3. You can also write our value. So we can do 6 double colon 3 double chevron, and then that is also equal to double chevron 6 double colon, and then you can type in size, open parentheses 3, closing parentheses, double chevron to close it off. These two bit strings are equivalent to each other. You just don't have to always write size. But if you want to be clear with your code, you can write size, and the Elixir compiler, Elixir shell, is always going to return size to us, like right here. So that is what a bit string looks like. And we can do things, we can combine 2 binary values to get a more readable bit string, right? So let's just do first equals, and we're just setting a variable first. And then we're going to set it to 0B110. And then we're going to set the size, so double colon 3, and then the closing double chevron there. Oh, and I did an O. We need a 0B there. So let's set that to our first variable. And then if we make a second variable and we do double chevron 0B 010, so this is just a value 2, right? And we're also going to make this the size 3 and then closing double chevron and then hit enter. So we have our first value that is 6 and our second value that is 2. Now, if we wanted to combine these, you can do something like this. We can do double chevron first and then double colon. And then we need to set the data type here. So we need to type in bitstring so the compiler knows what it's doing, and then comma, and then send in our second variable, and then double colon, and then also set the type to bitstring. And then we can do the double chevron to close out. And now I'm going to hit enter. And this might confuse you a little because we're taking a binary value of 6 and a binary value of 2. And then hitting enter, we now have a value of 50 and the bit size is 6. So it literally just took both values and stacked them together to make one binary value. If we just combine these, right? Our first value was 1, 1, 0, and then we just added on 0, 1, 0. So we put this value on the end of this value. And how do we get 50 out of that? Well, this equals 2. And then this would be 4, 8. This one equals 16. And this value equals 32. So if you add all these up, it equals 50. So we combined two different binary values that were only taking up 3 bits, and essentially we can store them within 1 byte. So we can store them in 6 bits, and 1 byte is 8 bits. So we still have 2 bits available, which is pretty cool. It allows us to combine 2 values. So if we were just to store them as integers, each integer would take a byte up. We'll go a little deeper into this as we get into our coding examples. Binary matching can also be used by itself to extract information from binaries. So we can do things like this. We can create a we can create a bit string with our double chevron, and we can type in hello, comma, space, double quotes, comma, and then we can then say name, double colon, and the type is binary, and then close out with the double chevron. And we can just set this equal to open quotation, hello, comma, space, Blork, closing quotation, and we can hit enter. So when we hit enter, we get a string back, hello, Blork. But what's really cool with this is we can grab the name because we have a variable set up above called name, right? So right here, we used pattern matching to set Blork to name. And we can just simply type in name down here, call that variable, and we get Blork out of it. To step up to be a little more complicated, we can also do things like this. So double chevron, we can do data underscore size, double colon, 40, comma, count, double colon, size, opening parentheses, data underscore size, closing parentheses, and then double chevron to close it. And then we can set it equal to, not double equal, we want to set it the variable. So equal to double chevron, 8, double colon, 40, comma, 3, double colon, 8. And then let's close it out with a double chevron. So what is going on here? What are we doing? We have we're using pattern matching to set some variables here. So we have a variable called data size that's going to be set to 8. And then we have a variable count that's going to be set to 3. All right. So when I hit enter here, we're going to get a funny looking bit string, right? What is going on? So we have a bunch of zeros here, right? 0, 0, 0. And then we have an 8 and a 3. So basically what happened is we have the data size. We set this to 8 and it's using 40 bytes. And 40 bytes, if you divide it by 8, equals 5. So we have 5 values here. So 1, 2, 3, 4, 5. So this value 8 is taking up these 8 bytes. But the value 8 can be taken care of within 1 byte. And so it's set to 8 and the rest are 0. And then we have the value 3 that is the size of 8 bits, which is 1 byte. And so value 3 is right there. Does that make sense? So essentially with these two values, we're just requiring 6 bytes. Okay. So 1 byte is 8 bits and 8 bits is what a typical binary value is. The binary data type is a specific type of bit string where the number of bits is divisible by 8. So all binaries are bit strings, but not all bit strings can be binaries. And just to run through a couple examples here, we can do something like this: is underscore bit string, opening parentheses, double chevron, 3 double colon, 4 double chevron, closing parentheses. We are using a kernel function to check if this is a bit string. So we have the value 3 and it takes up 4 bits. And we're going to get true back. This is a bit string. But now if we use a kernel function is binary and send in the same exact value, 3, and then the size of 4 bits, and then double chevron, closing parentheses, we're going to get false here. And the reason for that is 4 bits is not a binary value. A binary value has to have 8 bits. So we can also just to show you a couple more examples, let's do is bit string, double chevron, and we can send in a 0, 255, 42, and then double chevron, closing parentheses. We're also going to get a true here, like that is a bit string. And then we can also send those same values in to check to see if it's a binary. Is binary, double chevron, 0, 255, 42, double chevron, closing parentheses, hit enter, and that is true as well. And the reason for that is every value in this bit string is a byte. So if you don't state the size, it's assumed that it's 8 bits. So they're automatically 1 byte, and so that is binary. Now, if we also did something like this, is underscore binary, opening parentheses, double chevron, 42, double colon, 16, and then the closing double chevron, closing parentheses. This is also true because 16 is divisible by 8, so it's actually 2 bytes, and it is binary. Elixir also provides us with integer literals in different forms. So we can get the Unicode value that represents characters, and we can also get the integer value from binary. So if we did 0, B, 1, and then 1, 2, 3, 4, 5 zeros and another 1, we're going to get 65 back. So that equals 65. And if you're not sure how binary works, binary is, we have 8 bits, right? So 1, 2, 3, 4, 5, 6, 7, 8. This is value 1, 2, 4, 8, 16, 32, 64, and 128. Okay. So when we pass in a 7-digit binary value that goes up to 64, so we have this bit is on, and then we have 5 values 0, and then the first value is 1. So 64 plus 1 equals 65. So that's how that binary equals 65. Okay, and then if we wanted to know the Unicode value to a character, you just put a question mark in front of it. So if we did question mark capital A, that is also equal to 65. Pretty cool, right? Let's go ahead and jump straight into our project now. All right, let's expand the lib directory, double click on Bitstrings, and like always, delete our hello world function because we are writing our own code. I know you might be a little confused from just what we ran through with Bitstrings. So I threw together a little example that might help you understand the power behind them and why you might use them. They're obviously easier to read the value, like seeing a value 64, right? Versus trying to read 64 in binary. You'll have to count, every space. So just our brains don't really work to understand binary on the fly that easily. So with these examples, hopefully you can kind of see the power behind it and the kind of control we have with manipulating data using bit strings and binary, which is pretty cool. All right, so to jump into our project, Blork likes to automate his flying saucer movements as much as possible. He has written scripts for individual tasks and likes to use commands that call multiple scripts in order to complete the task he has to accomplish. The only problem is he has written so many, he is starting to run out of memory on his onboard computer. So we need to help him convert his readable commands to bit strings to cut down on the number of bytes his automated commands are using. So let's help Blork get started, and he can do the rest after we show him how to do it. I was talking to Blork, and a couple of his commands that he calls often is, so he has a fly to base command, and he scripts that as FB, okay? And then he has a fly to earth command, and his command for that one is FE. And then he has a hover command, and that is capital H. It's capital H. And then he has a tractor beam on command, which is capital T. And he has a tractor beam off command, which he uses capital O. All right, so he normally will do things like this. And I'm just writing in the comments so you can kind of just see what I'm talking about. He'll usually call multiple commands in a row to do a certain thing. So he'll call a character list, which is a single quote, not a double quote. A double quote is a string. A single quote is a character list. So that means each character is its own index in a list. But he'll call commands like fly to earth, hover, tractor beam on, tractor beam off, and then fly back to base. So he has, let's see how many this is. He has 1, 2, 3, 4, 5, 6, 7. So he has 7 bytes to call this command. So we're going to help him save a little space in his memory. I think we'll be able to cut it almost in half. He doesn't have more than 16 commands, okay? And right here, you see that he has, let's see, 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. He has 6 commands here. So he doesn't exceed 16 commands. So we can actually use 4 bits instead of 8 bits. And currently we're using 7 bytes, which is crazy. We don't need 7 bytes. So we're going to break down each command to use only 4 bits of the 8 bits. Does that make sense? All right. So let's first write a command that is going to encode each command to a binary value. And where I got 16 from, we're using binary, right? So it's base 2. And so 2 to the 4th is 16. So we have 16 different variations using 4 of the 8 bits. So we can do def encode underscore instruction and then send in our code underscore point, closing parentheses, do, and then end to close off the function. And we're going to use a case structure. We've learned this already. So case, and then our code point, do. And now you remember how we got our Unicode, right? We had a question mark in front of the character. So we're going to look, we're doing question mark capital H, and that is going to return a Boolean, a binary value, which we need 0B. And then we're just going to do 4 bits. So 0, 0, 0, 0. And that is what we're going to assign to his hover command. And these binary values don't mean, they mean exactly what we set them to. So you could set this to anything you want, but we're going to use 0, 0, 0, 0. And then we're going to create his fly command, which we're going to use F, because F, he uses fly to fly back to base and to fly to earth. So flying is going to return a binary value of 0001. All right. And then we're going to do his base. His base value is going to be capital B, and that's going to return 0B for binary and then 0010. And we're just going down. We're just going to knock the binary value up one increment each time we go through, because as Blork adds more commands, we're just doing 6 commands for him, but he can go up to 16 commands and he can just keep dialing them up. All right, and now we want to use capital E for our earth, and that's going to be 0B0100. And then we have our tractor beam on, which is capital T, and that's going to return 0B1000. And then we need to turn our tractor beam off, which is a capital O, and that is going to be 0B0011. So we integrated, or we kind of just cycled through all of our binary digits. And now when we pass in an individual command, so we'll just be passing in F or E, we'll get our binary equivalent to that, okay? So now we need to make a recursive function that will go through our char list of commands, get the binary value, and then we're going to combine them. Remember how we combined the 2 4-bit binaries in the Elixir shell? We're going to do the same thing here now. So we're essentially we're reducing one command from being a full 8 bits, and now 2 commands are going to fit in 1 byte, which is 8 bits. So that's pretty cool. Now we need to do our recursive encode function. So we're going to do def encode, and then we are going to be passing in our char list, which is the instructions. And then we are going to have our encoded value, which we'll be adding to over and over. This is a recursive function, right? So this is kind of like our accumulator. And we're going to set a default value here of a bit string with a value 0 and size 0. And this is going to be our header function because we are defining a default value. And now if we do our def encode our empty array or empty list function, we just do an empty array, and then we have our encoded value, which is our accumulator. And then we're just going to return our encoded value here. And this is our empty state. So when we get through our entire character list, we just return the encoded value. Now let's do our recursive piece where we do the head and tail notation. So now if we do encode, and then we pass in our list with head, pipe, tail, closing square bracket, comma, encoded value, do, and end. Now we essentially want to do our combine. We want to combine two binary values, and then we want to pass that back into our recursive function and just build on our encoded value, which is our accumulator. So we are going to just call our recursive function here, which is encode, okay? And we're passing the tail because the tail is the rest of the character list, okay? And head is the very first one. So we're passing the tail back in as our list, okay? And now this is kind of the tough part, right? We're going to build a bit string. So we need our double chevron, and we need to pass in our encoded value. And we have to declare the type as bit string, okay? And then we want a comma, and when we're combining with the head. So at first it's going to be size 0 bits, and we're going to add the head bit string version to it. And then that head moves over, and we just keep adding, and we'll be filling in the bytes with each command, and then we'll get our final bit string. So here we pass in, or we want to call our encode instruction function and pass in our head, closing parentheses, and then we want to do double colon 4 because we want to say the size of this is 4. Otherwise, by default, it'll set it to 8 bits. And up here, our encode instructions are just 4 bits. So we're passing this in, it's building the string, and then once the list is empty, we're going to return the bit string. So let's go ahead and go back to our terminal and recompile that code. And now if we do bitstrings.encode, opening parentheses, we want to pass in a charlist, which is a single quote. And let's do so fly to earth, hover, turn on the tractor beam, turn off the tractor beam, and then fly back to base. And then single quote for our charlist, closing parentheses. Now when we hit enter, we get a bit string that is only using, let's see, 1, 2, 3, 4 bytes. And one of the bytes is only half full. So we have a full 8 bits here, 8 bits here, 8 bits here, and then 4 bits. So we're using 3.5 bytes versus our 7 bytes. So Blork is going to be getting almost half his memory back, and he's going to be stoked. So that's pretty cool. The power we have with bit strings to manipulate and save memory space and just be more efficient with values. You don't always have to use an entire byte if you can get away with using less. And so we cut it in half using 4 bits instead of 8 bits, and that's pretty cool. With that being said, it's challenge time. As always, I want you to write documentation for all of our functions, write tests for all of our functions. And the third one, so Blork can no longer read his commands, even though they're saving him tons of memory. He needs you to write some code that decodes the bit string back to a readable command. So I want you to add a function decode instruction. So let's go back to our code. So essentially your decode instruction is just going to be the opposite of encode. So it's going to take a binary value and return the Unicode, okay? So you're going to take that, and then I want you to write a decode recursive function. So I want you to take, the decode instruction is going to be just like encode, but it's going to return the character list instead of the binary bit string. And so the decode will be a recursive function that returns a charlist instead of a bit string. So Blork can decode our bit strings to have the readable command so he knows what he's doing. As always, if you need help or want to check out the solutions, check out the GitHub link in the description. And if you have any more questions or just want to hang out and chat, join my Discord server, backend stuff. That link is also in the description. If you want to learn how to build scalable, production-ready APIs, hit that subscribe button now. See you next time.